So I know this seems like a lot of stuff, but I'll walk you through slowly, don't worry. First, you can press and hold Control and the mouse and scroll the mouse wheel to zoom in and out, and you can also press WASD to move the camera around. On the top right hand corner, there's a mini map to tell you exactly where you are on the map. So then over here, you can adjust the size of the playground, so that you can like set a smaller number of rows or increase the number of columns, but for now we just keep it at 25 and 50 by default. Most of our maps that we saved were saved in that format. Next is the draw mode. So by default you start with wall draw mode, so if you press and hold left click you will draw a wall, and if you press and hold right click you'll remove a wall. Let's just draw a few walls so it'll be more interesting for our entities to pathfind through. And now we go to the entities mode, which is when you left click, I think you can't hold this, you have to like click and release. When you left click entities you will summon them, and when you right click you'll remove them. So you also notice that like the black cells are walls and the gray cells are empty cells. So the light gray means that the cell is visible to the entity. The shaded or like the less bright gray cell refers to the cells that are currently in the fog of war. So like the entities have explored that before, but currently don't have vision. And then the darkest gray cell refers to cells that are unexplored. We will now start the simulation by setting a goal. Okay, the setting of goal is optional. If you don't, then the entities will just explore the entire map. And if you notice also over here it says enemy, that's because we initially wanted to do like an ally versus enemy kind of AI simulation, but that was way too overscoped for the amount of time we have, so we just went with this smaller pathfinding project instead. So let's do just that, and you'll notice that the entities will slowly make their way towards the goal. Even if they were started very close to one another, they still like split up, and that's because like we are using like a BFS method to find the goal, and the way the order in which we add like elements to the open list is random, so there adds a bit of randomness. So like the entities won't all just follow the exact same path, which is not only inefficient, it looks unrealistic. So so once one entity has found the goal, the rest of the entities will know exactly where it is and will try to pathfind it. Of course, if they haven't explored the area, that they might walk into a wall or something, and then they will just like reroute from there. You can also adjust these values, like over here you can see that this cone angle, I mean you can't really see well now because they are all at the same position. Okay, let's just purposely put the entities close to one another, and okay, I have to use these two, and you can see how like it changes. You can see how the arrows already changes, yeah, because of the repulsion field. If I increase this value, you can see that I did not mean to put so many entities there by accident. Let me just remove them. You can see how the arrows get affected. And let's just place another block of entities like over here. And you'll see what I mean by like the entities keep walking into walls, especially with a very big value for this. So let's just, where is it? Let's just set the goal to be like here or something. And start. Yeah, this is what I mean here. So with a smaller repulsion radius, it's not as noticeable, but of course if the map is also very narrow, then you get the same effect. Yeah, you can see that this guy's like stuck there. Yeah, if I turn this off, then you can see that the entities start moving normally again. Yeah, so this was like kind of to make the entities spread out, but honestly the randomness of BFS alone is kind of enough in most cases already. Yeah. So the reason that we chose vector pathfinding instead of like the traditional like A-star pathfinding from like each individual entity having its own pathfinding data is because of efficiency. Like if you have many entities, it's way more efficient for the map to store the pathfinding data, so that you only need to calculate once instead of once per entity. So to demonstrate that, let's just summon many entities and see whether like the FPS drops by a lot. So you can see currently the FPS is pretty high, and keep in mind that I am not even charging my laptop and I am also recording. So let's just spawn a bunch of entities, and let me turn off the repulsion field.
One eternity later.
Okay, I think this is enough entities. You can see that the FPS has dropped to below zero. Sorry, below 100 already, and that's not because of the pathfinding. That's probably because of the rendering and the other like calculations we are doing. But you see that once I start the simulation, it's actually quite smooth. Let's right click here and start. Yeah. And if I pause and enable repulsion field, you can see that it will not look very nice. uh, yeah, it will look quite crazy actually. So I'll now explain how a vector field and, or rather more commonly known as a flow field and the heat map works. So imagine we have a grid and we have a bunch of walls. Let's just, okay, imagine these blue shaded areas are the walls. And we have our start node, which is here, and our end node, which is, let's say here. So right off the bat, you can see that there's two paths that you can go from the start to the end, like either from here or here. And from here, you can't really tell which is the more efficient route, but we are not going to calculate that today because it's going to take too much time. In fact, let's just move this E closer so that I can show you how it works with the walls. Wait, actually, yeah, here. Okay, so first, I'll talk about the heat map first, and I'll go into how you can use the heat map to create the flow field. We have an open list. So this is using BFS. So you have a queue. Open list is a queue. Okay, I think that's how you spell queue. And then let's just put what is it? 5.2. Okay. 5.2 is basically our starting point. And we basically built a heat map from the end goal to every other cell. So basically, what this heat map represents is the distance from every other cell to the end node. That takes into account wall since it's BFS. So first, we pop this, and then we iterate through its neighbors. So what are its neighbors? This one, this one, this one, this one, and technically this is also a neighbor, like a diagonal neighbor. Okay. But since this neighbor is bordering at least one wall, we will not take that into account. Yeah, at least one orthogonal wall. So it's just these four neighbors, and we calculate the distance to these neighbors. So distance is 1.41. We are using Euclidean distance, but you can use like Manhattan distance, Chebyshev, doesn't really matter. These are the distances, and we also mark these cells as visited, even though we technically haven't popped them yet, we still mark them as visited. This visitation thing doesn't really matter, we're just updating distances anyway. And we add them into the open list, yeah. So, and then we repeat the same. So it doesn't really matter what order you add this into. Uh, you just pop the first thing here now. So now we're left with 6.1, 6.2, and 6.3. And then for this cell, its neighbors are this, but since this cell has an orthogonal neighbor, so we will not be adding that, we will not be counting that as a neighbor. So we don't want like the path to go like this. Yeah, we rather it go like this. Like similarly for this one, we obviously can't have the path go like this. So that's why we are not including the diagonal. So this will be 1, since this 1 is the distance from here to here, and but we also need to add this distance, which is the distance from here to the start node. So sorry, the end node. So 1 plus 1 is 2, and then here will be 1.41 plus 1, which is 2.41. And then we do the same for this also. We check. So since this already has a distance value, we just update it if it's smaller. So this to here is 1. So 1 plus 1 is larger than 1.41. So we do not update it. You only update it if it's smaller. So we just leave it as is, and we put these two nodes into the open list. So it's what, 5.0 and 6.0. So I won't be repeating these for like all the other cells. This will take too much time. You just get the drift. So this is how a heat map is calculated. But in our case, the entities do not have a vision of the goal node. So they do not have a target. They do not have an end because they do not know where the end is. They're trying to find the end. So what we do in that case is that we set every single unexplored cell to have a distance of 0. So let's say like these 3 cells are unexplored. We just set them to be 0. And then we do the distance calculation the same way. We add these 3 into the open list and mark them as visited, and we just repeat the same algorithm. So you get a heat map of like where things like further away will have a larger number. Yeah. Okay, so we calculate flow field for each individual cell. So like it can be something like this, and then like this, and this. Of course, it will be pointing towards the goal. And it will point around walls too. So how that works is that once you've calculated the heat map for the entire map, you have like distances like let's say 8, 7, 7. I just gonna call this 6. Like it's not this value is inaccurate, but like you get the point. 6, 5, 5, 4. And then we're using like a sliding window kind of technique. If you know like something like a convolution matrix, if you know what that is, this 3 by 3 area is to calculate the vector for this. Okay, we can like draw like an imaginary vector of each of the 8 cells around the middle cell away from the middle cell. Something like this. This just for visualization purposes. This is not actually what's happening. Yeah. So now we obviously want this cell to point towards a cell of lower value. So technically we want it to like point in this direction because this is 4. And you also need to calculate like the magnitude of that vector. So to do that, we can just take the sum of all this and average it out. But if we do that, then you'll notice that you point away from the 4. So to counter that, we just need to apply like a decreasing function. So like 1/8, 1/7 or something. So we can do 1/8 times this vector, which is, let's just say it's -1, -1, and plus 1/7 times 0, -1, and then so on and so forth. Yeah, so the last one will be like 1/4 times 1, 1, and you get like a vector for this value, yeah. And you just repeat that for all the other cells, and yeah, that's it. You get your flow field. Yeah, so now I would like to explain how our potential score or our potential map is calculated. It's used to have to make our entities prioritize unexplored areas more. So this hopefully improves the efficiency of the search. So before we start, we have to partition the map into blocks first. Currently it's by default it's set to 4, but for the purpose of this grid, it's easier if we just set the block size to 3. You will see why very shortly. So if the block size is 3, then we just split the map into like squares of 3 by 3. And this is like let's call this like 1 and call this block 2. And let's just say 1 has like 3 unexplored cells and 2 has 6 unexplored cells. And before we go any further, we also need to calculate the center of the block. So currently it's this is the center for block 1 and this is the center for block 2. Next, the number of unexplored cells, sorry. So for block 1, it will be 2, wait, 3, sorry, I cannot count. And for block 2, the number of unexplored cells is 6. Next, we check something. So the formula is if your unexplored cells is more than the minimum unknown percent, which is 0.625 times the block size squared, so 3 squared, which is 5.625. Well, this is not the case, so we do not continue. And then we go to the next block instead, which is block 2. And if 6 is more than 5.625, we go into a for loop. Okay, so basically we look through not just the cells in the block, but every single cell on the map, and we like accumulate a potential score based on the current block. So we first calculate the Manhattan distance from this to the block center, which is 1, 2, 3, 4, 5. Okay, So can do like a, let's say, int Manhattan distance equals to 5. And then we have another if check. So I don't know why that's in red, whatever. If this Manhattan distance is less than or equal to our maximum Manhattan distance, so this is like to make sure that like very far away cells do not also take like this cell into this block into consideration. Less than 30, is it? Yeah, 30. This is the maximum Manhattan distance. We calculate the new potential, like the potential to add on to accumulate to this current cell. The formula is max potential, which is I think I keep referring to this 0.25 minus Manhattan distance, which is 5 times max potential and 0.25 again, divided by the maximum Manhattan distance, which is 30. This will give me a while, 0.2083 repeating. You just append this to the cell's current potential score. Just keep in mind, like before this algorithm is run, the potential score of all the cells are reset to 0. Like this happens every frame. So cell dot, let's call it PS equals 0.208. I mean, since this is the first cell and this is like the first block that has any impact, the current potential score should be 0.208. Make sure that the values are standardized. We also normalize the values after the entire algorithm by simply dividing by the maximum potential score. I'll walk you through how I generated the random map. Basically, if you have default parameters, I'm just generating a perfect maze. And what a perfect maze is just a maze where there's only one way from one node to another node without backtracking. And I'm using a random walk algorithm, which just uses DFS under the hood. So I'll first initialize an empty open list, which uses a stack. Yeah, during the initialization phase, we'll set each of the nodes or each of the cells to be not a wall. So it's just a boolean is wall. We just set it to false, and we are also setting the is visited variable to false. And we also have another variable called parent. You'll learn more about that later. We just add this cell to the open list first. And just keep in mind that I'm writing the x and the y coordinate. So we now pop the first guy, and once you pop the first guy, we set the is visited variable to true, and we check its neighbors. So we don't check the immediate neighbor because you see later that we are going to remove, or we are going to set like the is wall variable to false, and we are also going to remove all walls that are between nodes. So if we did the directly adjacent neighbors, then every single cell will be a node, and every single cell will not be a wall. Yeah. So we have to take at least one cell away, and this distance is actually determined by the wall plus tunnel width parameter. The order does not matter. In fact, it's randomized so that the map generator is different every time, and we check whether it is visited. Currently, it's clearly not visited, so we just add them to the open list. It is 2, 0, and 0, 2. And we set the is parent variable. We set the parent variable to the original node. So this determines like the path from one node to another. So you might be wondering that this breaks the law of like the perfect maze because there's more than one path to one node. But just keep in mind that this parent is not fixed yet. It can still be changed in the future. And we pop the latest thing, which is 0, 2. 0, 2 is this guy. So we can set its is visited true, and once that is true, its parent cannot be changed also. So this path is fixed already, and it's likely that this will change. Rather, it's confirmed that this will change because this algorithm guarantees a perfect maze. So we add its neighbors, which will be 2, 2, and 0, 4. 2, 0, 4. Yep, we just set their parents to this, which are also not confirmed yet. And actually, let me do something different. Let me just change the order, and you'll see why later. I just want to show you something. And we pop 2, 2. So now we still have 2, 0 in the open list, 0, 4. And what neighbors does 2 have? Alright, before I do that, we confirm this and confirm this. So now 2 has this neighbor, as well as this. So this is getting added again. So now we have 2 4 4 2 and 2 0 again. And before we do that, we set their parents to this, and now you can see that how this changes to this. So finally, after all that, assuming that now we have completed the maze, we can see that there is a path, something like this. And everything else is not confirmed yet, so the confirmed path just looks like this, but assume that we have the entire map filled up already, and you have like a perfect maze. All of these cells or walls initially, so now we just remove we just treat these as not a wall, this as not a wall, this as not a wall. Basically, the arrows and the circles will no longer be walls. And if you take a look at the parameters, you might notice that there's something called wall width and tunnel width and stuff. So if you have like let's say a wall plus tunnel width of like 3, the nodes are 3 apart, let's say something like this, and the walls that will be removed will be something like this whole chunk, let's say for this. And there's also another parameter called min and max connections. So initially we have assumed that all of these have one connection. If you increase the number of connections, it will no longer be a perfect maze, because that means that there is more than one way to get to a node. So how that works is that at the start we initialize a random number from min to max connections for each of the cells, and this is basically like the number of connections it can make. So let's say initially, remember that this guy points here. Now let's say we are at this step, which is trying to add the parent. We check whether it has fulfilled its number of connections. So let's say this guy is allowed to make like 3 connections. So this is 1 connection already, so now it currently is at 2 connections. Since 2 is like greater than 0, it can still make connections. We will just append this to the parents list. So now parents is, you can think of it as a vector. I mean, it all along was using a vector. I was just like bluffing you, saying it was a variable because it was more easy to understand. So it will just push back another parent into here, and then when it's time to erase the walls, it will remove like this and make it no longer a perfect maze, but a more open one. And let's move on to the next parameter, which is a mean island size. And what an island is basically just a group of walls that are not bordering any other walls. So we can say that this is an island of 4 walls, and we can also say that 1 2 3, this is an island of 3 walls, and if we connect them, now this is an island of 11 walls. 10 walls, sorry, I can't count. And let me just remove this, and keep in mind that like diagonals do not count. So now let's begin the algorithm. It's actually also using DFS. In fact, in the code, I'm actually just using the same variable and just emptying the open list. First, you start with this cell. We check whether it's either a wall or it's not visited. So this is not a wall, so we just move next. And this is a wall and it's not visited, so we push it into the open list. So now open list has 1 0 in there, and we also initialize the current island, which is just a vector of pointers to all the walls in the island. So this is so that I have a reference to like set the is wall variable to false if the island doesn't meet the required size. Yeah. So this just starts off empty, so I'll just leave it in there, and then we'll start a while loop. So while open list.size yada yada yada, we will pop this and check whether it is visited. So it is not visited, so we will now add it to the island. So island now has the address of 1 0 in there, and we also set the is visited to true. And then next we get the neighbors. This time we are not getting like 1 cell away, we're just getting the direct neighbor, and we check whether it is a wall. So is this a wall? Nope. Is this a wall? Yes. If it is, we add it to the open list 2 0, Is this a wall? Yes, we add it to the open list, 1, 1, and we just repeat that for the rest of the wall. So it should be quite quick. So okay, let's just remove this so to make things quicker. So we just mark this as visited, and we push it back into the other vector, and then we get its neighbors. Okay, and then we pop to 1, mark it as visited, add it to the vector, and yep, I guess there's only 2 0 left. So now we just pop this and we mark it as visited, and we add it to the vector. So now once the open list is empty, it will exit the while loop, and now we check is the current island size less than the mean island size. So currently I have set the mean island size to 5, so yes, it is smaller, and it will set the east walls for like all of these to false. And now that all of these have been visited, it will go to this cell, and even though it is a wall, it has already been visited, so you just skip that and move on until it finds the next wall and repeat the same steps.